JavaScript is notoriously punishing for those who rely on assumption over mechanics. You can write an object method perfectly, verify that it works, and then watch the entire application fail simply because you assigned that same method to a separate variable. The terminal throws a type error, the internal object reference is gone, and the code collapses. This failure stems from a persistent misconception. Most developers assume the "this" keyword points directly to the physical location where the code is written in the file. The engine ignores where the function was authored. In JavaScript, this is a dynamic value calculated at the exact millisecond of execution. Every time a standard function is called, the interpreter silently passes a hidden argument into the execution environment, a context object. Isolating how the engine decides what that object should be is the dividing line between developers who write by trial and error and the engineers who architect reliable, bulletproof systems. To understand the engine's decision-making process, we have to look directly at the execution environment. The JavaScript interpreter relies on the call stack to manage the exact order of operations and memory constraints. When a standalone function is pushed onto the stack, the engine applies default binding. In modern strict mode JavaScript, it refuses to guess the context, leaving this completely undefined. But when you invoke a method attached to an object, the engine reads the syntax itself. The object sitting to the left of the dot operator is passed into the execution context as the this value. If you assign that method to an isolated variable, you sever the dot connection. Execution falls back to the default rules, and your specific object context is wiped out. The call site, the specific syntactic manner in which a function is triggered, is the engine's only source of truth. Those standard rules apply only until a higher priority operation interrupts them. The new keyword acts as an immediate override. When you use new, the engine executes a strict sequence. It constructs a blink object in memory, redirects the function's internal pointer straight to that blink object, and then executes the code block. This sequence takes absolute precedence. It overrides any implicit binding established by a dot operator. You can even verify this behavior from within the code. Using the new.target expression allows a function body to detect if it was invoked via this override. By forcing the creation of a brand new execution context, the new keyword turns a standard routine into a dedicated object factory. This strict call site logic creates a severe friction point when dealing with nested callbacks. If a method uses a helper function inside it, that inner function runs as a standalone invocation, instantly losing the parent's context. Historically, developers trapped the parent context by declaring a variable, often let self equals this, creating a manual closure so the inner function could find the right object. ES6 introduced arrow functions specifically to repair this architectural flaw. They do not possess their own internal this binding. Instead, they rely entirely on lexical scoping. Arrow functions reach upward through the environment, permanently inheriting the exact this value of their containing method. Because they lack a dedicated context slot to manipulate, the engine prohibits arrow functions from being invoked with the new keyword entirely. Arrow functions bypass the call site rule, ensuring the runtime execution perfectly matches how the code is visually nested on the screen. There are moments when you must override both default and implicit rules, dictating the context manually through indirect invocation. You achieve this using .call or .apply. These methods execute a function immediately, while force-feeding it a specific object to use as its context. For long-term control, there is hard binding. Calling .bind returns a completely new version of your function and permanently locks that context to your specified object. Even hard binding has strict limits. If you attempt to bind an arrow function, the engine simply ignores the command, preserving the lexical scope. Beyond locking context, .bind allows you to preset function arguments ahead of execution. This enables partial application, currying, which yields highly modular code. Explicit binding removes the engine's default logic entirely, granting you total sovereignty over how your code executes. The engine's resolution logic operates on a strict hierarchy. First, is it an arrow function bypassing the rules? If not, is the new keyword creating a fresh object? Is an explicit bind forcing the context? Is the dot operator implicitly passing it? And if all else fails, default binding takes over. The location where you declare a standard function is irrelevant. The call site dictates everything. Internalizing this hierarchy ends the cycle of guessing and checking. it provides the exact mechanical understanding needed to architect professional-grade systems that run precisely as intended.